Okay, in this lecture, we're going to cover section 5.2, and this is on the definite integral. So basically, what we're going to do is we're going to make these ideas that we developed in the previous section a lot more precise. So we talked about um, finding this area under this curve, and that was kind of the motivating problem for the integral. And so now we're going to try to make this idea precise, just in the same way where we talked about um, trying to make this idea of instantaneous velocity precise, and that led to this idea of a limit, and then the limit is now the foundation of calculus. That allowed us to define what it means to have it allowed us to define continuity of a function, allowed us to define differentiability of a function, and now it's going to allow us to define this notion of an integral, which is going to be very closely linked to this the idea of finding areas, which is what we looked at in the last section. So it's not going to always be the case that the area that the integral corresponds to an area. Um, but you can, in most cases, look at it, view it as computing the area, especially if your function that you're looking at is a positive function. It's always non-negative. In other cases, it might be some sort of like quote unquote signed area. So you can talk about negative areas and like how areas can kind of cancel each other out in a sense. We'll make that idea much more precise though. So let's look at let's try to just formulate all the ideas into a single rigorous formal definition. So let me share my screen. Okay. So this is 5.2. This is actually the definite integral. So there's going to be also there's going to be a definite integral, and this is going to be really closely tied to the notion of area, although it's not going to always be the same thing. And then there's going to be an indefinite integral, which we'll look at later. So here is the definition. So let's try to read through this and make some sense of it. It's going to be kind of complicated. So here's the definition. Sorry, my pen is not plugged in. So all right, there we go. Okay, so we have a function is going to be defined on an interval. So we have function f defined on a closed interval a comma b. Um, and then we want to divide this interval into n subintervals of equal width, just as we had done in the previous section. Basically, in the previous section, though, we were assuming all of our functions were positive on the interval of interest. So, but in this case, we're not necessarily assuming it. And so we have these n subintervals of equal width, and so if there are n of them, then the only width that they could have is this. This is like kind of forced upon you. You have to have this. They have to have this width because you have this. So you have the length of the interval b minus a divided by n. That's going to be their width. And so now we can take the endpoints of these intervals, or sorry, subintervals. So we could have x0, and that's going to just be the rightmost endpoint of the whole interval. And then we have xn, that's going to be the left. I'm sorry, x0 is going to be a, which is the leftmost endpoint of the whole entire interval. A comma to b, and then you have xn, which is going to be equal to b, and that's going to be the rightmost endpoint of the entire interval. And then you have some intermediate points, x1, x2, x2, xn, and these are going to be the endpoints, the right endpoints of the subintervals. And then what we're going to do is we're going to take some sample points, x1 star, x2 star, up to xn star, and these are going to be in the subintervals. So what that means is that xi star lies in this what you could call the ith subinterval. So this is going to be the ith subinterval right here. And then now, once you've kind of fixed all this collection of points, and this is going to be for every n. This is like for every n, this n right here. So you just like let n be arbitrary, just any arbitrary number, and then you're gonna pick these points, and then we're gonna define this right here, these symbols right here, this symbol right here, as this limit right here, which is exactly the limit we were looking at in the last section. So what you can think about this the way to think about this is that this is like the width of your rectangle, and then this is the would be the height of the ith rectangle in a sense. And now because your function can be positive or negative, this rectangle could be above the x-axis or it could be below the x-axis. Depends upon whether your function is positive or negative. But you can still interpret it as a height. It's like it could have a negative positive height if your function is positive, and then negative height if your function is negative. And then so you have the height times the width, and then I'll give you the area of the rectangle, the ith rectangle. And again, depending upon whether the height is positive or negative, that area could be positive or negative. So that's what we mean by a signed area. And then, so once you found the area of the ith rectangle, you're going to add them all up. So that's what this sigma is. Remember, this sigma means it's a compact notation for meaning you add up all these terms of this form. So all the terms that we're adding up are of this form right here, f of xi star times delta x. So you have basically and then finally what you're doing is you're going to take a limit because you want to take the limit as n goes to infinity because you want to have more and more and more division points. You want to divide this whole interval right here, a comma b, into more and more subintervals, and that's going to give you a better and better approximation of the actual area, or in this case, the signed area, because you could possibly have negative. This number that you compute on the right-hand side, I should say no, right, number on right-hand side could be negative. It could possibly be negative. Like for example, if the function is just always negative. So then you get this number, and then the integral right here, this thing on the left-hand side, is just defined to be this number. And so if the function is positive on the entire interval, that is just the area. It just gives you the area. But if it's not, it doesn't necessarily give you the area. And so now, so this is the definite integral of f from a to b. And it's defined to be this, and that's the case if the limit exists, and it has to be the same value. Notice there's a choice of sample points. So you need this to work for all possible choices of sample points. So that's a pretty strong requirement. So like you have these subintervals that you divide a comma b into, and you can choose any points in the subinterval. You could choose maybe so maybe you could choose the left endpoint as your sample point. You could choose the right endpoint, or maybe you could choose the midpoint of them, or some point three-quarter of the way, three-quarters of the way, or any other fraction of the way you want in this interval. So that has to work for every collection of sample points. So it's a very complicated definition, actually. When you get into more, as you go further along in more modern mathematics, like this can be simplified a little bit, like using different language in terms of like nets. So you have like you can talk about, instead of talking about convergence of like a sequence of convergence of numbers, you can talk about like convergence of nets. And so like you can take basically like these are your partition points in a sense. And so you like have these nets of partitions. And so you're taking like in a sense a limit over these partitions. But that's way beyond the scope of this course. And but there's a way of simplifying this definition if you have the right language and the vocabulary, basically. So there's a lot in this definition, and that's why this makes integration a bit more difficult because there's so much into packed in this definition. In fact, there's even more packed in because remember, this limit symbol itself has a lot of meaning in terms of epsilon and delta. So what this means is that this is what this definition means basically. It means when you actually write out what this means, it means that um there exists this number. So actually what it means is that there exists a number. They're actually missing part of the definition. So it means that there exists a number. Oh, I say well, okay, so if the limit does exist, we say that the function is integrable over this interval. And so this is not entirely accurate what they're saying down here. What I want to say is that if so we want to say f is integrable. So here's another way of phrasing this definition. F is integrable on this if there exists, oops, I need more room actually. So let's say f as a function from a to b to the real numbers is integrable if there exists a number denoted if denoted by these symbols right here such that and the number has this property right here for every epsilon there exists blah blah blah, and in fact this number is unique. You can show that if this number exists, this number is unique. It's the only number satisfying this property. So what it means, so what this definition says, let me zoom out a little bit so you can see everything. This whole complicated definition says that your function f from the interval a to b is integrable or integrable. I don't know how you say it. I've heard it both ways. If there exists a number denoted by this, such that it has the following property for every number or epsilon, there exists an integer n, such that this number that you is guaranteed to exist is within this approximation here. And so it's within epsilon units of this approximation right here for every subdivision n, where the number of subintervals you have is bigger than this capital N, and for every choice of sample points in each subinterval. So this is like a super complicated definition, and I don't expect you to be able to like understand this immediately, and that's perfectly fine. So this is definitely something that takes a lot to understand. There's a whole course that you take called analysis or real analysis, and it's where you go through and try to like make basically the whole course is devoted to just trying to understand this definition basically, and to like make sense of it and to like prove things about this definition. So for example, you'll prove in this if you take real analysis, which is kind of like calculus on steroids in a sense, you'll prove, for example, that this number right here is unique. That's like something you might prove in that course. Because it's not obvious that this number is unique. I mean, yeah, I'll just leave it like that. So what this says, again, just to read this again, it says that your function right here on this closed interval is integrable or integrable if there exists this number, which you denote by these symbols right here, such that it has the following property. That is the property that for every small distance epsilon, you can find a large enough integer capital N, and N is going to be like how many capital N is going to be like a lower bound on how many subintervals you need, such that this number is within this approximation right here. Because this is going to be like approximation, right? Remember, it was like you take a curve and you chop it up, the interval, into a finite number of pieces, and then you look at these rectangles maybe above or below the curve, and it approximates the area. And then it's going to approximate it to within epsilon units. And this has to hold for any partition where the number of subintervals in the partition n is bigger than that capital N. So you need at least that many subintervals, capital N, and then for every choice of points um, in the subintervals. And my computer's freezing now, which is unfortunate, even though I don't have any other windows open. All right, there we go. All right, so yeah, very complicated definition. Don't worry about it if you don't fully understand it. Um, just give yourself some grace. It's like I said, there's a whole course we're devoted to like trying to make sense of this idea of integration and looking at generalizations. There's another course you take called measure theory, where you have different ways of measuring sets. So this is one way of measuring the size of sets, basically. Um, so here's some just historical information. You have this symbol right here. This is like an elongated S to denote sum. It's the integral sign that was introduced by Leibniz. It's the integral sign, and it's basically to denote the fact that this thing right here is in a sense an infinite sum, right? That's what it is. You're taking um this sum right here. This is a finite sum of these areas of these rectangles, right? And then you're taking a limit as n goes to infinity. So you have like basically infinitely many terms in your sum. So it's an infinite sum. So that's why we use this notation here to kind of like, it's not literally an infinite sum, but it's like you can think of it as in a sense an infinite sum. Like that's maybe it isn't literally. Yeah, that gets a little, that kind of gets into like some philosophical issues actually, like that I don't want to talk about. I would love to talk about, but that they can get kind of complicated. So it is in a sense of infinite sum. You can think about it in that way. Um, all right, so that's the definition, some kind of no history, some explanation why we use this notation. Um, so well, yeah, so this is the notation. So your function, if you write this down right here, f is called the integrand. This is the thing that you're integrating. And then a and b are going to be called the limits of integration. So a is your lower limit, b is your upper limit, and so you're integrating the function from a to b, or you're integrating the function over the interval um a to b. So this symbol right here has no meaning in itself. Like you've kind of seen this, like with dy dx. I'm gonna When we get to u substitution, I'm gonna go over probably the section on differentials because that'll explain like what this means actually. It says it has no meaning, but it does. It does actually have meaning. So they're kind of lying to you. But this is like one symbol, it's a whole unit. And then this symbol right here means all this nonsense right here. So that's what it's meant to express. Um, But the DX does, what it does, one thing it does is indicate the independent variable of integration. So it's like telling you, like, we're integrating with respect to X, just as this means you are differentiating with respect to X. You're finding the rate at which Y is changing with respect to X. So it kind of means the same thing when you see this dx in this notation. It also tells you what things are constants because as you can imagine, well, maybe you can't imagine it yet, but what we'll see is that constants don't matter. Like if you take a constant multiple of a function, you can, in a sense, factor the constant out of the integral. All right, so here's just yeah, so this is just saying what we know what happens when this is positive. Oh yeah, I guess what they're saying is this right here is called a Riemann sum. This is named after the German mathematician Bernard Riemann, and he kind of came up with this idea. He kind of formalized this idea of integral um, into the sort of into the way we see it nowadays. So you're taking, in other words, the integral is going to be the limit of these Riemann sums. That's another way of phrasing it. The limit of these Riemann sums. And when the function is just positive everywhere, we know that these Riemann sums can be interpreted as the sum of areas approximating the areas of approximating rectangles. And these rectangles approximate the area under the curve. So you have like this is like a coarse approximation of the area under the curve. And then if you let n go to infinity in the definition, like we do in here, you're going to get better and better as n gets bigger and bigger and bigger. These Riemann sums, they approximate the area better and better and better, and they'll give you the actual area when you take the limit. All right, so, but now here's an important point. Most functions can be both positive and negative. So the Riemann sum is just going to be, it's like, it's not going to give you an area really. It's going to give you like a net. I think that what they say here, yeah, I guess they say it's a net area or like a signed area. So basically, like you have this curve. Now it's allowed to go below the x-axis. So these will have like negative areas. These will have positive areas, and so they like kind of combine and cancel each other out. And this is actually really important for applications. This fact it might seem like weird, but like for example, in physics, you talk about things like work, which is like the force applied to like a particle or some physical object over a distance. And the work will actually be an integral. It'll be like you're integrating the function as your force. So you have like maybe like the force of gravity or electromagnetic force or something, or force of friction. And that will be applied over some distance, maybe, or through time. And so that will um, what you want is that you want to work to be either positive or negative. So like work is like you can put some energy into a physical system, or say like maybe I push a box initially. So apply some force over some distance, and it transmits energy, and this is called work, which is, I don't know if that's really the best word, but that's what physicists use. It's just applying a force over a distance. So I impart energy into this physical system, say a box or something, and now this box is going to start sliding, and now there's an opposed force working in the opposite direction of its motion, and this is friction. So now it's losing energy. So it's losing energy. So we want to be able to subtract it. And so this might be like this negative part of the curve might be like the energy you're losing due to friction. So here's my initial push, this curve right here. This is the force you lose as you start sliding over surface with friction. And then maybe I give it another push because at this point it loses all of its energy. And now it's just stationary again, or something like that. I mean, this is not entirely accurate. But as I said, work is going to be this integral. So you want to be able to take into account that there are portions where you are applying positive work, and then portions where you're as negative work, so work is being done against you, and then there's points where work is positive. So you want to know what is the net work? Is it positive or negative? And so you find that by integrating your work function over a whole interval um, of time or distance or whatever. And so like it's possible that like these two areas, these positive areas could combine, and then the network is zero, like you didn't do anything to it. It lost all its energy. All the energy you put in was lost through friction, say. So yeah, this is just like me remembering vague, like, like hazily remembering or whatever. That's the word. That's not the word. My words aren't coming to me this morning. Very, they're not coming to me very well this morning. Um, but this is just like me like vaguely remembering some stuff from when I did physics as an undergrad. So don't quote me on all this as being entirely accurate, but that's the idea. So this is the indefinite integral is more generally interpreted as a net area, um, because the function could be positive or negative. Anyways, let's look at an example. Do we want to look at this example? Um, okay, so they want to just evaluate this Riemann sum. I guess this is kind of a dumb example, but let's quickly work through it. So you have this function x cubed minus 6x over this interval 0 to 3, and you want 6 subintervals, and then you want the sample points to be the right endpoints of these intervals. So first of all, if you have n is equal to 6, then and you want all the subintervals to have the same width, then the width is going to be delta x, which is 3 minus 0, the width, the length of the interval divided by the number of subintervals. So that'll be 1/2. So the width of each subinterval will be 1/2. And then um the the right endpoints, remember, they're going to be like of the form xi is equal to a plus delta a plus I delta x. So a in this case is 0, and then I can be 1, 2, 3, 4, 5, and 6, I guess. So then like x1 will be equal to 0 plus 1 times 1/2, which gives you the 0.5. X2 can be equal to 0 plus 2 times 1/2, which is 1, so that makes sense. And then x3 can be 0 plus 3 times 1/2, which is 3/2, so that's 1.5. So this makes sense. I just want to like go through these calculations. Remember, this is how you describe the right endpoints of the ith interval. So these are the rightmost most endpoints of ith subintervals. And you can go through the rest. I won't. So x4 would be 4 times 1/2, so plus 0, so it would be 2, etc. And then the Riemann sum is going to be this is by definition the Riemann sum. So always write when you're doing calculations for the first time, always write all your definitions out. So you can that's going to be the only way you memorize this stuff. So this is by definition, and then now we're just going to expand the sum. We're going to expand the sum. So you have f of x, this is x1, which we know is 0.5, this would be x2, f of x2, which is 1, f of x3, which is 1.5, f of x4, which is 2, f of x5, which is 2.5, and then f of x sub 6, which is 3. So x5, x4, x2, x3, x1, and then delta x throughout the whole thing, which you could just factor out really if you wanted to. And yeah, that's what they do right here. So there's the 1/2, factor it out because that's what delta x is. And then now plug these numbers into the function. So we're going to plug 0.5 into this function and then 1 into it. I guess you get, when you plug in 0.5, you get negative 2.875. Okay. When you plug in 1, yeah, you definitely get negative 5. Okay. And then when you plug in 1.5, you get this. When you plug in 2, you get 4. So when you plug in that one, we can do. So plug in 2 to this function, you get 8 minus 12, which would be negative 4, yeah. And then you get this one for plugging in 2.5. And when you plug in 3 of this, you get 27 minus 18, which would, yeah, it gets be 9. Overall, though, so when you compute this, you get a negative number. So what that means is that so here's the Riemann sum approximating well, it's not the net area, we'll say. It's not going to be the area because the curve can be negative. So what this means is that like the part of the curve below the x-axis, that area is bigger than the part of the curve above it. That makes sense. Like if you fill this area in, which is what we're trying to approximate, and then compare it to this area here, yeah, this area is a lot bigger than this. So overall, it's going to be negative. All right. So as you can see, these calculations are really annoying, and we want to eventually move away from having to do calculations like this, and we will. Let's see, do I want to look through this one? No. All right, so here's a want to be one of our first important theorems because so in this definition up here, we talked about what does it mean for a function to be integrable, right? It says if this horrible limit here exists and it satisfies all these properties, etc., then you say that the function is integrable on it here. And so you might wonder, okay, well, what functions are integrable? Like what functions can we integrate? And so this theorem down here tells us that the class of integrable functions is really big, actually. It's really huge. This theorem right here says that if your function is continuous, or it just only has a finite number of jump discontinuities, then the function is going to be integrable on the interval. That is, this number right here exists and it satisfies the properties in the definition. And this kind of makes sense if we think about f being positive. So let's just think about f being positive on this interval. So we have the continuous case, okay? So the continuous case would be like, let's say a to b. We're not going to prove this. Most of these theorems we're not going to prove because they're really complicated. But I'll try to at least make sense of these for you. So let's suppose I have a continuous function on this interval. So maybe it looks something like this. And it's positive, right? Well, in this case, um, the definite integral is just literally the area, right? And that area, this number exists. It's a finite number. So, this limit is going to exist. So it makes sense that that number, this number right here, is computable, that you can find it. So, for example, we can't have something like, because we're continuous, we can't have something like it go off to infinity and then it comes down here. This would be no longer continuous on this interval. And it would no longer be continuous, and actually the area would not exist because it's infinite. This is like precluded. We can't have this. This is not allowed. But so because we're continuous, we have a situation like this. We have this number exists. The area under the curve is well defined. But what about the other case? Jump. What about having jump discontinuities? Does that make sense? So let's look at that case. So we have like the continuous case and the jump discontinuity case. So in this case, maybe you're out for this interval a to b, and then you have like, maybe you look like this here, and then you jump up, and then you jump up here, and then you go like that or something like that. Maybe b is over here actually. And in this case, yeah, the area should exist. Like I should be able to drop a curve down here, drop a curve. I can just, this should be a solid circle. And then I can just like, to get the total area, I just need to like add up these chunks right here, right? So like I add this area, and then I add this area, and then this area. And this number right here, this definite integral represents the sum of these three areas, and all of which exist. So yeah, it makes sense that if your function just has a finite number of jump discontinuities, then you should be integrable. You should be able to integrate this function over this interval. So, and the class of continuous functions is huge, right? Basically every function we've looked at is continuous. So all of those functions will be continuous. And you can see though that the class of this example right here shows very clearly though that the class of continuous functions and the class of integrable functions is different. There are the class of integrable functions is a lot bigger. There are going to be functions which are integrable, say like this one, but are not continuous because this has jump discontinuities, so it's not going to be continuous. So basically we have this inclusion of functions. So we have the differentiable functions. So let's say, so talk about functions on some interval a comma b. So we have that the differentiable functions are contained. They're a subset of the continuous functions, and then this is contained in the integrable functions on that interval. Oops. But these are all strict, right? We know this now. We know that there are continuous functions which are not differentiable. So, for example, there's the absolute value function not differentiable at the origin, 0, but also there's that Weierstrass function, which is continuous everywhere, but not differentiable everywhere. So, so this is a proper subset. The differentiable functions is a proper subset, meaning that there are continuous functions which are not differentiable. But this inclusion right here is also proper because we know that there are integrable functions which are not continuous. So for example, this one right here, where you have disjunct discontinuities. So the class of integrable functions is way bigger than the continuous functions, and then so hence way bigger than the differentiable functions. So that's what makes integration a bit trickier, is because this is like the Wild West. There's going to be some really awful, nasty looking functions that you can still integrate, and so, but they're not continuous, so they don't have a lot of the nice properties that you want. So it makes it a little bit more challenging, or it can make it more challenging. All the functions we're going to look at though that we're going to integrate are basically continuous though. All right, so here's another nice theorem. What this says is that if you know that your function is integrable on this interval, say that you're able to argue this somehow, then this number you want to compute, you can compute it in this way, which doesn't look much different than what the definition said. However, the difference is that you can always take your delta x to be this, and you can always look at the right endpoints. Right endpoints of subintervals in the partition. Oops. Why that's nice is because if you go back to the definition up here, this definition says that this thing exists. Let me get rid of the sodas because it's pretty messy. That this number exists, this function is integrable if this limit exists, and it exists and it's the same number for any choice of sample points. What this theorem is saying is that if you know you're integrable, then you actually only need to use the right endpoints to get this number. So this is nice to know, because this is going to be end up being the easiest way to compute this integral right here. It's just using the right endpoints of your subdivision. All right, so let's look at this example. So let me open Paint so we can work through this in real time together. All right, so this is just to remind you, we're in section 5.2. This is 5.2 on the definite integral. So this is going to be example 2. And what we are asked is to express the limit. So this limit right here, the limit as of this Riemann sum. No, sorry, as I goes from 1 to n of xi cubed plus xi sine of xi delta x. So we want to express this as a definite integral of some function on the interval 0 to pi, 0 to pi. So in this case, this is actually not going to be that bad. We're going to say f of x is going to be x cubed plus x times sine x. And then note this is continuous. This is continuous. So it implies that it's integrable, I don't know. I have to look it up. So it makes sense to talk about the indefinite integral of this. And we have that a is equal to 0, b is equal to pi. I guess this was kind of a trivial example, but I'll just go through it anyways. So that means that if we integrate this function, x cubed plus x sine x dx, it's by definition this limit right here, the one we started with. So this wasn't actually as hard as I thought it would be to write down. Okay. All right. Let's see, where's another example? All right, so what we want to do now is evaluate, sorry, let's do example 3. So we're going to actually evaluate some of these integrals. So we want to evaluate the integral from 0 to 3 of x cubed minus 6x dx, which I think we looked at already. So first of all, no, x cubed minus 6x, let's actually call it f of x. Let's give it a name. So f of x, which is equal to x cubed minus 6x, is continuous. So it implies integrable. And then that implies that this makes sense. Like it makes sense to talk about this number because we have a continuous and therefore integrable function. So it makes sense to ask what is the integral? All right, so because it's integrable, we're going to use that theorem about computing it using the right endpoints. So by theorem 4, we know that we can take our width of our ith subinterval, and there's going to be n subintervals, as b minus a over n. Now b is going to be 3, a is going to be 0. So it's going to be 3 over n. And then the right endpoints of the subintervals are going to be xi, which is going to be a plus I delta x, but a is 0, and then we have delta I times delta x, so 3 over n. So it's just going to be 3i over n. That's how you're going to describe it. And this is going to be for I between 1, 2, and all the way up to n. All right, so then so now, well, just by the theorem, we can say that the integral from 0 to 3 of x cubed minus 6x dx is going to be equal to the limit as n goes to infinity of sigma, or the sum as I goes from 1 to n of f of xi delta x. Now we just plug things in, so we get the limit as n goes to infinity of delta sigma I from 1 to n of f of 3i, and then delta x, which is 3 over n. So you can see this is really annoying. And so we eventually want to we want to move away from computing integrals in this way. And we'll come up with some tools and techniques for doing that. So now we're going to plug in, we're going to evaluate our function at 3i over n. So, and first of all, we have this constant right here. Notice that this right here doesn't involve I. The variable for this sum is I. So we can factor that out right there. So we're going to have 3 over n. And then we're going to evaluate this. This is going to be 3i over n cubed minus 6 times 3i over n. And then taking a limit as n goes to infinity of 3n. Now we can't take this n out of the limit because it's like we have these two variables. We have like I, which is the variable for the sum, and then we have n, which is the variable for the limit. So we can't take this 3n completely out of the limit. We can't put it here. We could take the 3, but there's no point. Just leave the 3 there. All right, so now let's see if we can simplify a little bit more. So we're going to get now 27 over I cubed and cubed. And then minus, let's see, if you simplify this, it's going to give you 18 over I n. Okay. And then let's see. Hopefully there aren't too many examples like this. This is really tedious. And then let's see, what do they do now? Oh, okay, so now we have so I'm gonna actually pull the book up because there's a bunch of rules we're gonna use that I didn't show you. So we have some rules for um computing sums. So this one we actually saw in the first video, but it turns out there's like some other ones. So if you want to take the sum of the numbers from 1 to n, so this right here would be equal to 1 plus 2 plus 3 up to plus n. It's the same thing as computing this right here. Okay. And then you have a formula for computing cubes, which we're going to need. This one we're going to need right here. If you want to take the sum of if you want to take the first cubes of the first n numbers and then sum them together, you can. It's the same thing as evaluating this on the right hand side, which is kind of interesting. It's like basically this formula but squared. So I don't really know why. I haven't really thought about that, but that's interesting. So this thing right here, if you expand that, it'd be like 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed. And it equals this thing right here. We're going to use this because we have a I cubed in our formula. And then there's some other ones that we already used this one actually. If you have a scalar multiple, so we had 3 over n, you can just factor it out. And if you take a sum of that AI plus BI, you can like distribute the sum over that, and the same thing with the difference. Let me actually just like kind of justify this one a little bit. So basically, if you take the sum of I as I goes from 1 to n of AI plus BI, what is that? Well, it's going to be AI1 plus BI plus AI2. Sorry, it's going to be A1 plus B1 plus A2 plus B2 all the way up to AN plus BN. So like you can put these parentheses around here if you want to like bracket them off. And then what you do is you just use the commutativity and associativity of real numbers. So you have an AI here, A1 here, A2, AN. So just put all those together. So use commutativity to put all the A's together, the A terms together, but bracket them off. And then do the same thing with the B's. Put the B terms together, B1 plus B2 up to Bn. And then this will just be equal to this sum as I goes from 1 to n of AI plus sum as I goes from 1 to n of BI. So that's why this one's true right here. And we're going to use that too. All right, so let's go back here. So I'm going to distribute and I'm going to factor some stuff out. So let's see. So I'm going to distribute the sum first. So I get 27i cubed. Notice there's an I cubed, so I definitely need that one formula. And this is from I goes from 1 to n, and then we have minus sum as I goes from 1 to n of 18i over n. And then now just copy everything down. Now I have some scalars. So I have 27 over n cubed. So I can do 27 over n cubed. Sum as I goes from 1 to n of I cubed minus 18 over n as a sum as I goes from 1 to n of just I. And then if you consult those formulas that I just showed you, we can replace this sum and this sum with the following. So we're going to have, let's see, it's going to be, well, I'm going to also distribute this through. So let me do that. So if you distribute this through to this term and then to this term, you're going to get 81 over n to the fourth. And now I'm going to replace this by, what you replace it by is n plus 1 over 2 squared. And then minus, so now I'm going to distribute this to this. This is going to be 54 over n squared. And now this gets replaced by n, so this is times, and sorry, it's going to be, this is times n plus 1 over 2. Maybe I should have used like a parenthesis here. All right, so now, if you, oof, this is really crazy, isn't it? All right, so it's not that bad actually. So it's a little bad, but not that bad. So now I have this 81. I'm just going to leave this, and now I'm going to so I square the numerator and the denominator. Actually, so I have this 4, 2. So I'm going to square that. So I'll have 81 over 4, and then I'll have n squared over n plus 1 squared over n to the fourth minus 54 over 2 times n plus 1 over n squared. I'm going to use that same trick that I used. I got to actually, yeah, look at all that just for this one example. So yeah, these calculations can be really awful. So I definitely don't want to do a lot of these if we don't have to. Of course, I mean, some of these steps you might be able to skip over. I just want to like go through all of them just because this is a very involved process. So some of them you could kind of combine together probably. Just don't make sure you don't exclude all the steps. So I'm going to use a trick I used in the last video. So I have n to the fourth, so I can break it as n squared times n squared. So that when n squared will cancel with this one, and then I can divide the n squared into this. So when you do that, you're gonna, let me just write it down. So you're gonna just do this, then you have n squared. So I canceled out a factor of n squared. Now I have this n, so I'm gonna divide, cancel the factor of n, so I'll just have n plus 1 over n. Limit as n goes to infinity. And now I have like a square, so I can like take the square of the whole thing. And what this will be then, and then I divide the n into the n, and then n to the 1, so I get 1 plus 1 over n squared minus 54 over 2 times 1 plus 1 over n. And now I can finally take a limit, because when I know, well, it's because when n goes to infinity, 1 over n goes to 0, and then 1 over n goes to 0. So this is going to be now 81. This whole term is going to be 1 plus 0, so it's going to be 1 squared, which will still be 1. And this is going to be 1 plus 0, so what I'm left with is 81 over 4 minus 54 over 2. And when you combine those, you get negative 27 over 4. Ooh, that was crazy. So very annoying, very tedious. And so this is like motivation for us to want to develop some techniques for integration, improve some more general results, so we don't have to do calculations like this every time we come across the integral. All right, so I'm going to skip 4. I encourage you to look at it because actually, let's just look at it together. I won't go through all the calculations. So just another illustration of how awful these calculations can be. And in fact, with our current tools, we can't even calculate this. We have to rely on a computer. Eventually, though, we will be able to calculate this. So here's an example. This one will be very easy to calculate once we know the fundamental theorem of calculus, which links differentiation and integration together. So we want to set up an expression for this integral as a limit of sums. So first of all, e to the x is continuous, therefore it's integrable. So we have f of x is equal to e to x. This is continuous. You have a is 1, b is 3. So that means we can use theorem 4 to calculate this integral right here, which was about computing things using these right endpoints. Computing the integral via this limit using right endpoints, not just any sample points. And then the subintervals will have this width right here. All right, so where is it now? Oh, it's right here. So a is equal to 1, b is equal to 3. So delta x is going to be b minus a over n, which is going to simplify to 2n. And then these are going to be so your right endpoints are going to be, this is a plus I delta x. And then by theorem 4, this integral of e to the x over the interval 1 to 3 is going to be this horrible limit here. And then so as the limit of n as n goes to infinity of the sum as I goes from 1 to n of f of xi delta x. But f of xi is just this, so you plug that into the function, and then delta x is 2 over n. So you can factor out the 2 over the n, and then now plug in 1 plus 2i over n into the function, so you get this part right here. So this is looking really awful. And now this you can't even do anything with this. You have to ask your computer algebra system to simplify this. Or compute this sum, I should say, to evaluate the sum and simplify. And now you got to take a limit of this thing times this 2 over n to get the to compute this limit. Sorry, I lost track of what I was saying. So you use a computer algebra system to evaluate the sum and simplify. So now this integral right here becomes this limit of 2 over n times this horrible thing here that the computer algebra system got for us. And I guess when you do that, yeah, you can sort of see it. So, no, not really, actually. It's kind of horrible. Yeah, well, it ends up being, when you ask the computer algebra system to evaluate it, it ends up being that. So that's really awful. But here's the short answer by the fundamental theorem of calculus. Since since the derivative of e dx is e dx, that i.e. e dx is its own antiderivative, the integral from 1 to 3 of e to the x dx is just e to the x evaluated at the top endpoint minus e to the x evaluated at the bottom. Done. So this is going to be huge motivation to want to understand what the fundamental theorem of calculus is and how to prove it. Because once you know the fundamental theorem of calculus, evaluating this limit is literally one line, and that all rests on the fact that e to the x is its own antiderivative. What the fundamental theorem says, the calculus says, is that if you have a function, you want to integrate it, and you have an antiderivative then of the function, that is a function which when you differentiate it, gives you the function you started with, then to evaluate the integral, you just evaluate the antiderivative, which is exactly what we did here. And that kind of pops up over here as well. But you would not be able to tell that that's how you compute integrals in general based on this horrible calculation. Like this is really, really awful. We want to move away from this. All right, let's see what else do we have. I don't know if we really have much more. Oh, see, here's going to be some properties of integrals. I'm going to skip this. Um, I'll just briefly say what it said. I'll just briefly read it, but I'm not going to go over in detail. So another way to evaluate integrals is to interpret them as areas. So here's this function, it's continuous, and you're considering the function over the interval 0 to 1. So 0 to 1. But so the function is positive, and you can actually, if you plot this, it's like a quarter of a circle. So the area bounded is a quarter of the circle. So that's why it's going to be a quarter of the circle with radius 1. So this integral is just going to be the area of a circle divided by 4, because you're taking a quarter of the circle. So if you can interpret some of these curves as corresponding to geometric shapes whose areas we know how to compute, then these integrals can simplify a bit. Same thing with like this one. If you want to integrate this function 1 x minus 1 over 0 to 3, so this interval here, this is x minus 1 is going to be the line that passes through this point and goes up like this and this. So there's like these two parts, like there's this part where the function's below the x-axis and above it. And you can chop up the integral at this part right here. And the pieces that you have are just two triangles, and we know how to compute their areas. So you have A1, which is going to be this positive area, and then you have A2, which is going to be a negative. That's why there's this negative here, because you're going to subtract off that rectangle from, you want to subtract that part off right there. All right, so that's not much to do there. So if you don't fully well, yeah, I mean, there's just not much to do there. So read through that if you want to. All right, so here's where we get to some properties of integrals that are going to be really useful. So the first one is, well, they didn't put it in this box here, but this one says that if you want to, yeah, so when we're defining this integral right here, we're actually assuming that a is less than b, because we're talking about a function on the interval a comma b, and we're going to integrate the function over there. But you can actually make sense of this limit of these Riemann sums, even if a is bigger than b. So what happens in that case then is that delta x in the definition changes from this to this. And then what you can do is you can factor out a -1 from this, and you get this expression right here, this relationship. So in other words, what it says is if you want to integrate from b to a, it's the same thing as integrating from a to b, but just throwing a negative sign in there to like reverse things. And then this one says that if you integrate a function over an interval with no width, like there's no length to the interval, then your integral better be 0, because you're not talking about any area at all, right? You're talking about if you want to integrate a function, suppose you have this function right here, and it looks something like this, and you have a single point A, and then you're looking at the area over this interval under this curve. You're talking about like a line right here, and lines have length, but they have no width, so they don't have an area. So this integral better be 0. And also, it's just due to the fact that when you compute delta x, it's going to be 0. So you're when you go back to this definition up here, or even theorem 4, let's say, um, or theorem 4 right here. This delta x right here is going to be 0. So you have 0 times the height, 0. And so then you're adding up a bunch of zeros, which is 0. And then you're taking a limit of 0, which is 0. So that's why everything cancels out that way. And then this says, so you have a number property 1. So if a is a constant, and if you want to integrate a constant function, it's just going to be the constant times the length of the interval. And this kind of makes sense. If you just imagine that your constant is positive and you graph it, you graph this constant function, it's always at the same height. And what you're looking at is the area under this curve, but it's just a rectangle, right? So you need the length of the base, which is a minus b, times the height, which is just c. So that one should hopefully make some sense there. And then 2 is hopefully pretty reasonably true, and that's because if you take the sum of two things, I mean, not even try to explain it in words. There's a proof. It's very trivial. It's right here. So if you have if f and g are integrable, then by theorem 4, you can calculate the integral in this way. But this sum right here, we know distribute. Well, first of all, this delta x, you can distribute it to the g of x and then the f of x. So you get this. And then this sum right here, you can distribute it over this sum right there. And then the limit of a sum is the sum of the limits. But this right here is by theorem 4, the integral of f of x. And then this limit right here is the integral of g of x. So the reason why you can distribute the integral over the sum is because you can distribute this sigma over the sums, basically. So the integral shares, which we can think of as an infinite sum, shares a lot of properties that finite sums have. It has a lot of properties in common. Let's see, what else do we have? All right, so I'm gonna just do, let's see, let's do this example right here in using these properties. So we want to evaluate this integral right here. So what we can do is we can distribute the integral over this sum right here. So we have the integral of a constant 4 plus this integral of 3x squared. Now this 3 right here, I can factor out of the integral. So I've so far used this property, and now I'm going to use this property here where I can factor out a constant. And then so now I have this 3 right here. And now when you integrate 4, this is by property 1, the integral of 4 over this interval is just 4 times the length of it. So it'll just be 4 because the length of the interval from 0 to 1 is 1. And now I have this 3 times this integral, and this integral we calculated in the first lecture, or the first video, the previous video. We found that it was equal to 1/3. So overall, then we can compute this integral. It'll be the integral of this integral plus this integral. It'll be 4 times 3 times 1/3, so it'll be 5. So here's another nice property. It says that if you have an integral and you have some point C that is between A and B, so here's a picture, you can basically add the areas together. You can, like, if you want, so in other words, the area of a whole is the sum of its parts, basically. So area is like additive. So if I want to just chop up the area at this point right here at C, I can do that. I can just add this area. So I can find this area and then this area individually and then add them together to get the whole area. So I'm gonna just skip B. And then here's another. I don't know how much this is gonna come up a lot. I don't know if this is gonna come up a whole lot, but here's some properties of integrals. These are comparison properties. So this one kind of makes sense. Like if you have a function and if the function is positive, then what this says is that its integral is positive because you're talking about an area. And then 7 is actually follows immediately from 6. And that's because this inequality implies that f of x minus g of x is non-negative. So then when you can integrate it, so this will imply that the integral of f of x minus g of x dx is going to be positive over this interval a to b, and then I can distribute the integral symbol over this difference like this, and then I can add the integral of g of x to both sides to finally get that the integral of f of x over a comma a to b is greater than or equal to the integral of g of x over the interval a b. Yeah, so that will prove that. And then 8, so 7 follows from 6, and then 8 follows from 7. And I think that's all we're going to do. Oh, so yeah, here's the proof of property 8. All right, so that's all we have for this video. I mean, I encourage you to read through this proof. It's not that hard. It's not that long even. It's pretty easy. And then I encourage you to look through 9 as well. So that's all we have for this video.